Well, I know you guys probably don't read your book. Okay, so we're gonna review a little bit over 3.4. So remember how we did an example about enlarging circles? This was example 1. I will scroll up. Oh my God, enlarging circles, etc., etc. So that was pretty interesting, but like you're probably wondering, where does this actually come into play in real life? So first, 3.4, what we started yesterday and what we're going to finish today, it's all about applications of derivatives. So where do you actually see it in real life? So for example, a physician, maybe a doctor, wants to know how it changed.
Oh, I thought it was a P, sorry. What?
A P?
A fly, I thought it was a... Oh, ew. It's like huge for a fly, sorry.
What am I?
I like so bad. Can you kill it?
Okay, cool. So
I'm kind of lazy.
this is, okay, let's keep going. So if you're a doctor, if you're like in the medical field, maybe, or whatever, maybe you're a pharmacist, what you need to know is how does a little bit of a change of dosage, change a body's response to a drug, right? So also if you are going to be a business major, maybe study economics. I am so tired. Economy. This is if you're gonna be an maybe you're wondering like, okay, so what's the cost? Like with producing steel, like how does the amount of steel we're producing, how many tons, how does it, like the cost of producing it change with a little bit increase in supply and demand?
Just kill it.
It's like mass scale production. Sometimes it's cheaper to make more than to make it low cost. So for instance, making food for one person is probably not that much cheaper than making food for 2 people, because it's like, oh, you have to have salt, you have to have pepper, like all these one time. So different derivatives, it's literally these rates of change. All right, so you see those little circles on the left side. The top one, so it's kind of, we're going to talk about growth rings on a tree, and this includes example 1 where we had like, as the radius changes, how does the area overall change? So this example right here, the rate of change in area of a circle with respect to its radius gets larger as the radius gets larger. All right, so as the radius gets bigger, the area of the circle gets bigger as well, like you know that. So this is reflected in nature in many ways. When trees grow, they add layers of wood directly under the inner bark during growing season, then form a darker protective layer for protection during the winter. So you guys have probably seen tree rings before. Yeah. So the results in concentric rings that can be seen in a cross-sectional slice of the trunk. The age can be found by counting the rings. So which one actually is a better model for tree rings, the top one or the bottom one? The bottom. It looks more like an actual tree ring. So the deal is, if you look, we know the bottom is a better pattern of tree. Because if you look at the top, thank you. If you look at the top, it has the same change of radius every year. It's like, okay, it'll increase by 1 inch every year, but that means the area is getting more and more and more, meaning it's getting more light, more nutrients, more growth, amount of growth every year. Like that's not sustainable. That's not real life. It will probably grow about the same amount every single year. Maybe if it's more rainy, it'll grow more. Maybe if it's a fire, like it will grow a little bit less. But if you look at a tree ring, they get closer and closer as you go outer. So I thought that was pretty interesting. Another one, this right side, it's showing the rate of change. So you can see where these balls are with respect to time. It's like every, 5 milliseconds or something, they took a picture and they're all overlaid. So maybe you saw this in physics. Don't say yes or no. I don't care. I'm just saying maybe you saw it. I don't need your complaints, whatever. All right. So maybe you saw it. So if you notice at the top, the distance between these 2 balls, it's not much. But as we get further down, the distance gets bigger and bigger, which means it's speeding up. It's covering more distance per single time because all of these pictures are spaced evenly apart. So it's increasing, it's accelerating. The velocity, the speed, how fast it's going is increasing because it's covering more distance per time. And if you look at the rate at how much the distance is increasing, the amount it's increasing is also increasing. So if you have position, how position is changing is velocity. That's your speed, your velocity, how fast you're going. But if you want to talk about how the rate of change is changing, So, okay, so I'm going from 60 miles an hour to 70. That is a change of 10 miles per hour per minute or whatever I'm accelerating at. So your change with respect to change is also a derivative. So we talked about that last time. And a sensitivity to change. So in a small change in x, this is straight from the book. I just copy pasted it because it's very interesting. Maybe it's not interesting to you, but it's important. Okay. It gives you context. Like, a lot of times you study calculus or math and you're like, this has no impact in my life. This has all the impact in your life. I know every single one of you has a phone. Phones would not be possible without calculus. You're like, what? How? Because literally, yeah, and okay, whatever. Sensitivity to change. When a small change in x produces a large change in a function value, we say it's relatively sensitive to changes of x. Because if you change it just by a little bit, if it like varies and goes off, it's very sensitive. So this derivative tells you how sensitive your function is. The more it's changing, the higher the slope, the more sensitivity you have. And then derivatives in economics. Engineers, we talk about velocity, we talk about acceleration as derivatives of function. So velocity is the first derivative of position. Acceleration is the second derivative of position. If you're studying economics, they have a specialized vocabulary for rates of change and derivatives. They're called marginals. And so the derivative of a marginal is your marginal cost of production. So if you have how much it's going to cost you to make steel beams or whatever, if you want to know, well, how is the change of cost of production? That is your, oh my God, I'm not even talking right. You can read. My point is showing you, like, it's not just where I have studied it. It is everywhere in your life. Fun fact, 70% of MIT undergrads that study physics go to Wall Street and work at Wall Street, yeah.
How many percent?
70% of physics majors. I almost doubled. I was planetary science. Instead of doing 2 more classes and doubling in physics, I decided to do 8 classes and get a credential in high school physics. Okay. It's just like, like 2020 is coming up. Having clear vision, looking back. Okay, so my point in showing you this is physicists, they didn't go and just didn't study money. What they did was study problem solving. They studied in-depth, higher level math. And so you use this math to create a model of what the heck is going on in the stock market. Yes.
I don't know.
Yeah, well, no one does.
Keeps dropping.
Okay, so my point is there's many uses for calculus. I'm trying to bring them in to make it, I don't know, a little more interesting, but also cool. So now that we've done a little bit of review, now let's go on and try to finish this. And I'm going to read a little more when we hit section 5. We're going to finish section 5 today, review all day Thursday. Cool. All right, so, what? Yeah, let's do this. What?
Wow.
Okay.
Someone's taking
What? Are you logged in? Nope, I did not even begin the class. That makes sense.
The class began.
Yes. If you want to get out of press test mode, there's a lock.
And then whenever I open it, it says that thing where
Yeah. All right, go ahead, log in. Let's do this. Example 3, DTHS. Example 3, a particle moving along a line, so that's position at any time t is greater than 0, is given by the function s of t, where s is measured in meters and t is in seconds. Find the displacement of the particle during the first 2 seconds. Okay, so displacement is literally you take final position minus initial. During the first 2 seconds, our first time is 0. Our second time is 2. So what we're going to do is take s of t2 and minus s of t1. Literally taking final position minus initial. So if I want to find the final position, what? I don't understand you guys. Plug in 2. So I'm gonna do it. Don't worry. When I have a break. What? No, that's the average velocity, which is the next. No, it's yeah. What? Right now? Oh my god.
I wouldn't
Tall.
bother you if you made this week.
I know.
How are you?
Okay, so let's go ahead and let's plug in. What is S of 2? 4 minus 8 plus 3.
-4 plus 3 is -1.
-1.
How do you know that?
Minus 3 equals -4. So the displacement is -4 meters.
Well, come on.
Okay, now.
Wait, isn't it plus 3?
No, because it's subtracting 3, so you're minus 3.
Minus.
It says plus 3.
Yeah, oh god, okay.
Yeah, but it's minus 1.
Alright, ready? I'm going to show you. Let's find S of 2. This is equal 2 squared minus 4 times 2 plus 3. 4 minus 8 plus 3 is going to be -1.
Yeah.
Stop talking! What is your problem? Be quiet, I'm explaining this.
Oh, and then you did S.
Oh my god, okay. That is 0 squared minus 4 times 0 plus 3. This is going to be 3. Sorry, plus 3 is 3. So if I'm taking -1 minus a positive 3, it's going to be -4. Okay, now find the average velocity during the first 4 seconds. Notice we have a difference. So now we will find the displacement. Remember, it's displacement over time. So we need to find S of 4. Go ahead, plug in, see what S of 4 is equal to. I should probably email Elliot and warn him that I yelled on the screencast. It'll be so loud.
0.
All right, let's see. S of 4, so 4 squared minus 4 times 4. Because on top is meters, on bottom is time. So 0 meters per second. So average velocity, on top you have position, which is measured in meters. Bottom is time, which is in seconds. So it's meters per second. Good luck. All right. Now we have average velocity. We want to find the instantaneous velocity. Instantaneous velocity. So what would be great is to find the velocity equation. Then I can just plug in my time, figure out what the velocity is at that moment. How do I find velocity from a position equation? Velocity is the first derivative of position. So I have to find the derivative. So I need to do d dt of the equation that's at the top, which is t squared minus 4t plus 3. So what is my velocity equation?
2t
minus 4. We're just using the power rule. So if that's the equation for velocity, we want to know what's the velocity when time equals 4. So plug in 4 for t. Four meters per second. If you're done writing this, try out D. Find the acceleration when t equals 4. Hint, it's going to be similar to the process we used with C. Think, how does acceleration relate to velocity?
Are you gonna, are we gonna memorize these things? That, velocity?
No, I'm not giving you the formulas. I literally spent 5 minutes today saying I'm not giving you the formulas because I moved the test.
We have to memorize average velocity is the derivative of whatever.
Velocity is derivative of position and acceleration is derivative of velocity.
And then
so I need to take the derivative of velocity, 2t minus 4. Using the power rule, what's my derivative? 2. So wait, does it matter if I plug in 4? What is a of 4? Still 2. And what is the units? Meters per second squared. How many of you guys have not taken physics or are not enrolled in physics? Will not have taken physics yet? Just 1? 2? 2? Okay.
Also,
You didn't take physics last year and it's not this year? Question.
So, how do you know That it's 2.
So plug in 4 for t. There's no t. It doesn't depend on t.
Oh, no, how do you know the acceleration is 2?
So I took the derivative of my velocity equation. 2t minus 4, take the derivative with respect to t. Derivative of 2t is 2. Derivative of negative 4, since it's constant, 0.
Oh.
Okay, yes.
Quick question. For taking the derivative of something, the exponent, it always goes
You
to the
bring it down, multiply, and then you subtract 1 from the exponent. So technically this is 2 times t to the 0. Sorry, 1 times 2 times t to the 0. But t to the 0 is the same thing as 1. So I just
So
goes
if
away.
up there it was like t
Squared.
cubed or something,
Yeah.
would it be 2t squared?
So it'd be 6t
Oh,
squared.
6t
Yeah.
squared because you were.
Yep. All right, so now let's describe the motion of the particle. So we have all this information, right? So during the first 2 seconds, it goes back 4 meters. The average velocity during the first 4 seconds is 0 meters per second. And then we know that the acceleration at 4 seconds is 2 meters per second, which is going positive. So let's describe the motion of the particle. At what values of t does the particle change direction? All right, so what we really want to do when it's describing the motion, we want to look at our velocity equation. So we know v of t, we found it, was 2t minus 4. And so remember our example yesterday. So we throw something up in the air. When did it change direction?
When it gets to the
When-
top.
When it gets to the top, what's the velocity at the top? 0. So we're going to switch directions when velocity is equal to 0. So we set it equal to 0. And we solve for the time where we switch directions.
Would you want us to leave it like as, like, are you okay with us leaving it as t equals 2, or would you rather it be like t equals 2 seconds or 2 seconds or?
So we want to describe the full motion of the particle. So we figured out when it stopped. So if it's, okay. So I'm going to show you like the way I want you to write it. That's a good question. All right, so we know between 0 and 2 seconds, what are we doing? Going backwards. So the position is going negative. After 2 seconds, what are we doing? Going forward. So our velocity is positive. All right, so this is, I'm talking about what is my velocity with respect to time. I mean, ish. Like I'm just trying to describe what's the velocity when we're at these times. At 0 seconds to 2, we're going negative velocity. 2 seconds to 4, we're having positive velocity.
How do you know that?
So at 2 seconds, our velocity is 0.
Yeah.
And we know at 4 seconds, our velocity is 4. If I plug in 1 for time, what's 2 minus 4? Negative, right? So it's negative. Any number between 0 and 2, if I plug it in, would give me a negative number.
Oh, so you just plug them in your head to see that.
Yeah.
Okay.
So I know at 2 seconds, I will have 0 velocity. And since I already had a number to the right, I plugged in 4 at part C. I knew I'm positive on the left. And we said on A, we knew our displacement was negative, so we were like going backwards, so that's a negative. Okay, so if we want to describe the motion of the particle moving right from 2 to infinity, do we remember our parentheses and square brackets, right? Because at 2 seconds, we're switching directions. So at that very small instant, we're not moving at all. And we are moving left from 0 to 2. And there's this funky thing, right? Look, we haven't included 2 at all. So we say, and stopped at t equals 2. So this would be an excellent way to describe the motion. So describe the motion, I'm saying when it's going right, because going to the right is positive, going to left, negative, and when you're stopped is literally when your velocity was 0. So I have, I don't know if we'll get to it today, I have a review of section 3 and 4, where like we go through more problems like this. And lastly, particle motion. So these are now the position time graphs. Hey, we're going through position time graphs now. So, a particle moves on a number line shown in part A. So it's just moving back and forth. But what we can do is show the position as a function of time. So although the particle is just moving in one dimension, the right graph is actually showing you, okay, at this time, where am I at? At this time, where am I at? So when are we moving to the left? When are we moving to the right? And when are we standing still? So we have three things to look for: left, right, and standing still. How can we tell if something is standing still?
It's velocity 0.
The velocity is 0. So how does the velocity relate to a position time graph?
Whenever it's like whenever it doesn't change.
Like at 1 to 2 and 3 to
Or no change
Slope. We're looking at slope. To find velocity from a position time graph, we're looking at the slope. So if we're standing still, that means a slope of 0. We're standing still whenever the slope is 0. So I'm just going to put that slope equals 0. What about when we're moving to the right? How do I know when I am moving? Positive velocity, so that means a positive slope. And if I'm moving to the left, that means my slope is negative. So all I have to do is go up to the graph, find the slope of each portion. So first, for this section right here, what is the slope?
positive. Right.
It's, well, I mean, we can find the actual number. It's 2. Slope equals 2, because rise 2, run 1. Oh my god. All right, right. What about this portion right here? 0 slope. Right here, this is down 4, run 1. So this is a slope of negative 4. So to find that, I just did a rise over run. I went down 4 over 1. Then I have a slope of 0, and lastly a slope of negative 2. So let's think. When am I moving to the right? Do you guys want to try this out first, or you just want to go over it together? Give me 5 seconds. I'll give you 5 seconds. Try to figure it out. So at the two ends, at the very, very ends, that's where you can use a bracket.
Okay. But everywhere else is parentheses because you're not actually like.
Yeah, because that's like the boundary point.
Okay. Do you use a union?
Yes, you're gonna have to use a union. So when am I going to left? When do I have a negative slope?
2,3 union 5,6.
Beautiful. And end bracket, because that's the very, very end of our graph, is 6. Moving to the right is going to be a positive slope. There's only one place where we have a positive slope. Let's see. So notice the only... No, it stops at 1. So we only have our bracket at 0 and 6 because it's the very, very ends. All the stuff in the middle, we have parentheses. And lastly, standing still is when I have a slope of 0.
1 to 2 union 3 to 5.
Exactly. So.
Like 3 to 5 or left. It doesn't have to be like there could just be a whole bunch of space in it. Never mind. My question doesn't make any sense. I'm good.
Okay.
Yeah.
Cool.
Okay.
Okay.
Yeah. I think I know.
Okay. It's just like when we're writing like domains where we're positive, blah blah blah. Like we just take the sections where it's 0. We take the sections, and the union is you just take all the sections, squish it all together. So we have one answer.
Oh, okay.
That's all union does. Is like, hey, put it all together. Okay. So now we want to graph the particle's velocity and speed where defined. So wait, we went through and we found the slopes. Surprise, already did most of the work for you. We've gone over graphing this before, but we're going to take another shot. So I'm just, oh my god, it's so slow. Okay, there we go. All right, so velocity. We already found the slopes. Literally what we're doing is we're taking the values of the slopes, graphing them on the velocity time graph. So between 0 and 1, our slope was 2. So we include the endpoint, we don't include the switch off. What was the next slope value? 0. Wait, when were we standing still? From time 1 to 2. 1 to 2. And now if you look back, I hope it, is it going right? Cool. Okay, now we're going to graph our slope of -4. And it's going to be a value of -4 from 2 to 3 seconds. -4 from 2 to 3. Try the last 2 by yourself. Yes. All right, so we graphed our slopes. These are the velocity time. How is speed and velocity related? Speed is the scalar version. It's the absolute magnitude. So literally, I'm going to copy this left graph over, but everywhere it was negative, I'm now going to graph it positive. Because before I had a velocity of -4, speed doesn't have a direction. Speed's always positive.
It's the absolute value.
Exactly, it's the absolute value. Because on my speedometer, I can be going 60 miles an hour forward, that's positive. I can be going 60 miles an hour backwards, that's a negative velocity. Still, 60 miles an hour is my speed. Speed's always positive.
Why would the one on the left for VT, why would that one be shaded?
So the two endpoints are shaded. At 0 and 6. At 0 and 6.
Like right here.
The beginning and end point of my, the beginning and end is always like filled in, included, inclusive, brackets. All right, so from 2, okay, so I just copy what I had before, except for when I get to the negative. Absolute value -4 is 4. So then I'm going to go up to 4, go back to 0. Absolute value -2 is 2. So that's the difference. We just take whatever was negative, and now we take absolute value and make it positive. Because speed is the absolute value of velocity. Cool, so that's it for section 4. Section 5 is relatively short. Blessed. All right. So, section 5. Before we look, I'm just going to read this to you, and then we're going to do a little thing on our calculator. Oh my god, load. All right, so derivative of the sine function. Trig functions are important because so many of the phenomena we want information for are periodic. Heart rhythms, earthquakes, tides, weather, literally the signal on your phone. How, when you call your mom to say, come get you early, how does she know what you're saying? Literally, your voice is translated into sound waves, which go and hit the receiver, which is converted into electrical impulses, which have a form of a wave function, which is trig, which is sine functions. There you go, literally every day. This is why we're going over it. It's known that continuous periodic functions can always be expressed in terms of sines and cosines, so the derivatives are a key role, because what if you want to know how something's changing? You have to take the derivative of sine or cosine. So this section is all about derivatives of the 6 basic functions. You will have to memorize these 2, and we're going to be using them a lot. Oh my, I just wrote an M. I don't know why it did not work. You have to memorize these both. Okay, so how do we know the derivative of sine is cosine? Let's go look. All right. So I'm going to open up the calculators, and I go to my graph. So I'm going to put in sine of x. Surprise, this is what sine looks like. No surprise at all. If I want to graph the derivative, how do I go about doing this? Hit the little template key to the right of 9, go over where it says derivative, put an x down here, and then I can put in f 1 of x, which is my first function. Okay, so when I'm looking at the derivative, how does it compare to sine?
It shifted one.
It shifted over. But wait, if I just had the red on there, what does it look like? It's literally a cosine function.
Oh.
Surprise! Derivative of sine is cosine. Okay. Yeah, I mean, maybe. Okay, what if I change it? What if instead of sine, I have cosine? What's the derivative of cosine? Ooh, look at the red now. So blue was my cosine. This is negative sine. It's the reflection of sine. So if you look at the blue, the red is the derivative. So remember, sine starts at 0, goes up to max, 0, min, 0. This red is totally opposite. Instead of going up to a max, it goes down to a min. Back to 0.
Oh,
it's opposite.
I get it.
So let's go back to the notes. This is why derivative of sine is cosine, but the derivative of cosine is negative sine. Okay, let's try this out. I don't know, I just thought it'd be better if I showed you in the calculator so you can like see it instead of just telling you because you're like, what the heck? Okay, so y equals x squared times sine x. So we have to find the derivative of this function. I have x squared times sine x. So I have two functions being multiplied. I have the product of two functions. So I have to use the product rule. Yeah, do you see how I have two functions being multiplied? Yeah, so I'm going to let x squared be my u function. I'm going to let sine of x be my v.
Bless you.
And if you remember, product rule, u dv plus v, oh my god, I always do this, du. Little primes are the derivative. So you take the first function times the derivative of the second and add the product of the second function times the derivative of the first. So what I normally do, I normally literally write it out so I don't confuse myself. Just so it's as easy as possible so I can just plug in and go. What's the derivative of x squared? 2x.
Sorry, that was...
V is sine. It's okay, you're just one step ahead. Derivative of sine is cosine. So now I can just plug in. I know what each of these are. The hardest part was realizing this is a product of functions and I must do product rule. So, I just put a new battery in. I don't know. What the? Okay. Cool. All right, so y prime, which is the first derivative, is going to be equal to u, which is x squared, times v squared, which is cosine x, plus v sine of x, times u prime, which is 2x. So I'm going to write it as 2x times sine x. And then that's it. That's it. I can't simplify it anymore. I'm done. Okay. You okay? Okay, just make sure. Okay, were you here when I graphed? Okay, cool. Just make sure. So derivative of sine is just cosine, and then derivative of cosine is negative sine. All right, how do we feel about this one? Product rule. Yeah, let's keep going. Okay. I'm gonna leave this up here for a second. So look at your paper and look at B. Y equals cosine x over 1 minus sine x. So notice I'm dividing two things, so I have to use the two words. Quotient rule. Dividing is quotient rule. I'm taking two functions dividing. Okay. So okay. So let's see. I'm gonna let this be
X squared.
what? So here's my high. This one's my low. I wrote.
You get that on recording, please say it.
Yeah, it's recording. Okay. Okay. So. Okay, so quotient rule. All right. This is crazy. But if I put in my little dongle thing for the HDMI, like it won't record the screencast. So Elliot and Tall is gone right now, so quotient rule. Okay, do you remember it? Low, D high. Take, which is minus. High, D low. Cross the line and square the low. Low, D high, take high, D low. Cross the line and square the low. Sorry, it's kind of hard to read. So D low clearly is derivative of the low. Cool. Yeah, just grab your calculator. All right, so we know what high is. We know what the low is, more or less. What's wrong? I told him he can come in. It's all fine. We're good.
Thank you.
It's bananas. Yeah. All right, so high is cosine x. What is D high?
Sine X.
Negative sine x. Low is 1 minus sine of x. Be kind. D low, what's the derivative of the low? Okay, derivative of 1 is 0. Okay, what's the derivative of sine? Is cosine. But don't forget we have a negative 1 in front of the sine, so negative 1 times cosine, so it's negative cosine.
Yeah, I thought since it's negative sine x, we just put it straight into cosine.
No, so if you have negative sine x, you take the integral, it would be cosine. But since you're taking the derivative, okay. So you have negative 1 times the derivative of sine. Because remember, this negative 1 is the coefficient right here. Negative sine x is literally negative 1 times sine x. So you're taking negative 1 times the derivative of sine.
Oh,
so negative 1 times cosine is just negative cosine.
Okay.
All right. Okay, so let's fill in. Whew. So dy dx is equal to low 1 minus sine x times d high, which is negative sine x. Subtract high, which is cosine x. Am I out of room? Oh my god, I'm so stupid. Okay. Minus. Okay. I can make it. Okay. So then, 0 minus cosine x is just negative cosine x. Negative cosine x. Too close to the edge. Negative cosine x. Have you guys filled this in already? You don't have to wait for me. You wrote down the equation and then you take the low and square it. Okay, you know what? I've told you 50 times that... Okay. I told you like 50 times how it's like not being great. Okay, now it's just all about simplifying. I'm going to distribute the negative sine x. Okay, you know what? Let me draw the color so you like see me distribute this out. Okay. So I have negative sine x plus sine squared x plus cosine squared x all over. I'm just going to leave it as 1 minus sine x squared.
Why don't you use sine x squared? Just use sine squared x.
Wait, what?
It's not sine x squared, it's sine square x.
Oh, got it. Okay. Yeah. So you're talking about this part right here. Okay, so sine of x squared is the same thing as sine squared x. It's not, I'm not taking sine of x squared, I'm taking sine of x squared. No, you didn't look at my hands. Ready? Let's try it again. I'm not taking sine of x squared, I'm taking sine of x and then squaring it. Nope, didn't do it for you. Okay.
Sine of x and then square.
I'm not taking sine of x squared. This is not the same thing. I'm taking the whole sine of x and then squaring it. Yeah, okay. Okay, so how much of chapter 5 of pre-cal do we remember? Sine squared x plus cosine squared x is?
Oh!
1. 1. It's equal to 1. Okay. 1. It's equal to 1. Pythagorean identity. Pythagorean identity.
1 minus sin x over 1 minus.
1 minus. It is. So wait, why did I not like FOIL out the bottom? Oh my gosh, guess what? So negative sine x plus 1, same thing as 1 minus sine x. Right? Negative sine x minus 1, same thing as 1 minus sine x. How does the top and bottom compare?
1 over 1 minus sine x.
Beautiful. Beautiful. Because I can cancel out the factor on top and one of the factors on bottom. Hey. It's wonderful.
This stuff isn't on my calculator, right?
What do you mean?
Like if I put sine squared x.
No, because you don't have the variable x defined, so it won't do it for you.
Will it find it for you?
That's a mischievous smile.
It is.
She knows it can, we just don't know how.
Exactly.
It can?
What?
Yeah, I'm not going to say how. Not
Before
now.
I go to college, will you show me?
Yeah, of course.
Wait, it does do it though. Google what's your account.
Yeah, but you know what's really funny? When you have
Test mode on, it doesn't let it.
I can exactly limit what you do.
Oh.
It's like I know what I'm doing here. Oh my god. All right, let's keep going. Okay, so what? Cool. Okay. I don't know. You said simple harmonic motion. Here we go. Is there anything I wanted to read to you out of this? There were some like interesting things. I'm probably.
You did the one thing earlier and that's about it.
Okay. All right. So now, hush. So now that we know sine function is differentiable, we know that sine and its derivative obey all rules for differentiation. Wait, let me repeat that again because you're talking. You're talking. Stop talking. Now that we know the sine function is differentiable, we graphed it. Did you see any holes? No, because the derivative is cosine. We know cosine is continuous. Goes on both directions forever. Thank you, pre-calculus. We know sine and its derivative obey all rules for differentiation. We also know sine of x is continuous. The same rule holds for all the other trig functions. Each one's differentiable at every point in its domain, so each one's continuous at every point in its domain, and differentiation rules apply for each one. Perfect.
Tangent's not continuous.
Yes, but sine and cosine.
Oh, okay.
Yeah. All right, so something interesting. Maybe you've been wondering, why do we use radians exclusively in calculus? Maybe you didn't ask that.
I didn't even know that was a thing.
But my pre-calculus students this year are keeping like, can I just use degree? No, you need to know radians so you're fluent. So when you go to calculus, you can use radians. So radian measures in calculus. In case you've been wondering why calculus uses radian measure when the rest of the world seems to measure angles in degrees, you're now ready to understand the answer. You ready? Yeah. Life-changing. The derivative of sine of x is cosine of x only if x is in radians. Okay, so if you look at the analytical confirmation, you're going to see it's literally, I'm literally reading the textbook out loud to you because I know you don't read it yourself. What does that mean? No, it's true. No, it's true. So I'm just.
No student like that.
Yeah, honestly, I'm not going to read the textbook about it.
I'm taking a break from homework. I'm going to go read like
I swear to God, I'm the only person that reads the books here.
Question, why are we using AP?
What?
Why are we using AP textbook?
Because it's excellent, and I don't test you to the level of an AP. Right. Because it's very intuitive. So you notice the problems I assign you are normally towards the front end, not the back end. So I'm more AP. The beginning of the questions are easier than the So I think they're done with chapter 4 already. They're going through more stuff than we do. Okay, so cosine x times the limit as h approaches 0. H approaches 0 of sine x over h. Do we remember when we did something like this, sine x over x? Remember the limit?
It's 1. It is 1. You cancel out h.
Yes, but, are you ready? If you look at The derivative of sine x is cosine x only if x is measured in radians. If you look what I just wrote, you see this is what the derivative is, right? Derivative of sine of x is cosine x, and then you multiply. It's like we're trying to use the product rule, but literally what is the limit as h approaches 0 of sine h over h? It's 1. So this is because it's in radian mode. If you look at the same limit in degree mode, it's going to get very, very different. Hence, we're going to be using radians. Do not ask if it's degree. In your calculator, you must be in radian. That's all I'm going to say about that.
Why can I
You know what?
Head out?
You know what? That's not. I guess it wasn't as powerful for you, but it's
Can I
fine.
take the head off? The head? The head?
Sure, you do you. Simple harmonic motion. The motion of a weight bobbing up and down at the end of a spring is an example of simple harmonic motion. It has a period. It goes back and forth. We can model it by sine.
But my calculator radius.
You should be in radians. A weight hanging from a spring is stretched 5 units beyond the rest position, s equals 0, and release at time equals 0 to bob up and down. Cool. I am reading this so you can listen and look at the same time. What the heck? Its position at any later time, here's our equation, s equals 5 cosine t. What is its velocity and acceleration? Literally what we have to do is find the derivative. V of t is the first derivative. What is the derivative of 5 times cosine t? 5 times, what's the derivative of cosine t? Negative sine t. Right, derivative of cosine, negative sine.
The t doesn't go away.
No, because it's v of t, it's with respect to t.
How come it's parentheses with the 5?
Because I'm doing the variable, the constant that's in front of it, times the derivative.
Oh, yeah.
Yeah, so 5 times negative 5 sine t. So this is sine of t. And if I want acceleration, you have to take the derivative of negative 5t squared. The derivative of sine is cosine. Nope, it's negative, yeah. All right, and the next part is, I thought I was talking about jerk. I think we already talked about jerk. Jerk is the the derivative with respect to time of acceleration, derivative of acceleration. So the cool thing is, other trig functions can be derived using the derivatives of sine and cosine. So literally all you have to know is sine and cosine. Derivative of sine, go. Derivative of sine?
Cosine.
Derivative of cosine.
Negative.
Cool. Wait, what's tangent in terms of sine and cosine?
It's sine over cosine.
Exactly. Guess what? We're going to find the derivative of
Did
tangent.
we just cosine over sine?
So, ready? Tangent. Oh my god, it can work. Okay, so so tangent is just sine over cosine. Interesting. This is quotient rule. Quotient rule. We need to find quotient rule. Okay.
Equals x.
So my height is sine. What is d high? Cosine. Derivative of sine, cosine. My low is cosine. What is d low? What's the derivative of cosine?
Sine.
Negative sine. Okay. So if I'm wanting to find the derivative, I can use the quotient rule. dy dx is going to be equal to
Cosine x times cosine x minus.
what's the word? What's the song?
High D low minus low D low.
Okay. I think you have it backwards.
What?
I think you have it backwards.
This is just changed.
It's low D high.
I'm aware.
Low D high.
But I'm confident.
It's low D high.
Low D high over high D low. No.
Low D high. Take high D low. Cross the line. Square the low. Low D high. Okay. So cosine x times cosine x. Shh. Unless one of you want to come up here and teach it, I'm expecting you to be quiet and listen. If you have a question, raise your hand. If you want to explain something, raise your hand. Right? It's like fine if you're explaining it. I can literally hear when you're talking what you're talking about. I'm not deaf. I'm not 60 years old. Pay attention. If you're going to describe, help each other with questions, that's fine. Just don't be off topic. Why? Why did I move the test? Makes me so mad. Okay, minus, high. Well, high is sine. And then you're trying to multiply by d low, which is going to be a negative sign. All over, across the line, and square the low. The low is cosine, so it's going to be cosine squared x. All right, so simplify the top out.
Cosine squared x minus the negative sine squared x.
But the negative in front of sine, and then we have negative sine. Cosine squared x plus sine squared x. So this whole portion right here is equal to 1. So that's just 1 over cosine squared x. What is this in terms of an actual like trig function, not with a fraction? Secant squared x. It's equal to secant squared x. So guess what? You just found dx of tan x. Literally, the derivative of tangent is equal to secant squared x. Awesome. Here are the, oh, surprise, it was literally right here the whole time. Cool. All right, the other derivatives. Derivative of secant is just going to be secant times tangent. You could literally put derivative of 1 over cosine. And then you do quotient rule. And you will find it is secant x tan x. If you want to find cotangent of x, well, guess what? You just flip the high and the low, and then go through the whole thing, and you'll find it's negative cosecant squared x. Similarly, like all of these, you can literally use product rule, or quotient rule for all 4 of these, and find it what it is.
For the last one, what if you had crossed out cosines?
You can't, because there's a plus here. This is a binomial. You can't just cross out cosine squared x. Because there's a plus sign in between, you have to like keep those stuck together. All right, last thing. What? No.
Really? You can cross it out and use minus?
Oh, sorry, because cosine squared x minus sine x is not equal to 1, so you can't actually replace it with 1.
Oh, but
if there's a minus in between, you still can't cross it out.
But what if you're multiplying them?
If you're multiplying them, then you can cross out a factor. That's fine. Okay, so treat it like there's parentheses. Yeah, treat it like there's parentheses, because it's a binomial. They're stuck together.
So cosine
Sorry, I didn't hear your question right yet.
Cosine squared x
plus sine squared x is the Pythagorean identity. It's equal to 1.
So that's just something else we have to add.
That was chapter 5, section 1 of last year. Pythagorean theorem.
Okay.
Yeah. So if you have your pre-calculus notes, like, cool. Just probably, I don't know, look over them. All right, find the equations for the lines that are tangent and normal to the graph of f of x equals tan x over x at x equals 2. Okay, first, try to find the equation for lines. Well, first, why don't we find the slope? So tangent is literally just going to be the regular slope, and normal is the perpendicular. So we need to find the derivative. Once we find the derivative equation, we can plug in the value for x. All right, and then we'll find the slope at that value, and to find the perpendicular, we flip it and change the plus and minus to the opposite way. The negative reciprocal or whatever, opposite reciprocal, that's what they call it. And then once I have the slope, well, we know x equals 2, I plug in 2 into the equation to find the y value, and then we plug in the slope, point slope. Yeah, that's a lot. There's like 5 different things you have to do for this problem. Just thought I'd warn you. First, we want to find the derivative of f of x. So, notice I have tan of x over x. Once again, we're using the quotient rule. I don't know why this is not writing. So, f prime of x. So, I'm using the quotient rule. So, high is going to be, this is my high, this is my low. So I'm taking low, d high, so low is x times low, d high, so low is x times d high, so what's the derivative of tan of x? Secant squared x, okay, minus high, d low, so high is tan x, what's the derivative of x? On the bottom, what's the derivative? 1. cross the line and square the low. All right, can I simplify this at all? I mean, secant squared x is the same thing as 1 over cosine squared x.
That doesn't do anything.
Right, it doesn't really help us. Okay, so you know what? We're going to leave this equation as it is, and we are going to use our calculators. So, you know what? Let's go and let's find f prime of 2. So, I have 2 times, I'm going to rewrite secant squared x as 1 over cosine, and I'm just going to put 2 here and then put the square on the outside. It's the same thing.
Can we leave it as well?
Yeah, but if you look, it's going to look a little confusing because I have it squared, and then I'm taking 2 right here. Why did the square go away? Right? Because that looks, it is what it is, whatever. Minus tan of 2 all over 2 squared. Yikes. So you plug it into your calculator. This is approximately going to equal, actually plug it into your calculator, see what you get. I don't know why it's not working. And then to find the normal, what you're going to do, change, so since this was positive, I'll make the normal be negative, and you take the reciprocal. Yeah, this is not going to be a nice point slope function. Welcome. Welcome to the real world, where the numbers are not nice and round. This is more like it. Okay. So, we found the tangent slope. We found the normal slope. The last thing we have to do is find the value of the function at 2. And then we just plug it in. So this is where we'll end on Thursday. We'll have to, so I'm going to write the equations. Thursday we'll finish the last one. It's very fast. And we'll review. So if I want the tangent, I'm just going to write the tangent and the normal. I'm pretty sure you could plug it in yourself, but whatever. So y plus 1093 equals 3.433 times x minus 2. And then lastly, y plus 1093 equals negative 0.29 times x minus 2. Not the best, but it is what it is. But you can leave it in point slope. That is perfectly fine. All right, so Thursday, make sure you bring your practice tests. Just review the whole time. Lots and lots of review.